Okay, so in this problem, we have a particle P, which has a weight of 2 pounds, which is able to slide on a smooth, light rate horizontal arm that is rotating about a vertical axis. We're told that initially P is stationary relative to the arm, and the axis is rotating at a rate of omega 1, and that P is a distance r from the axis of rotation. We're asked to then determine the angular speed of the arm when P is moved outward to a position of greater r, as measured from the axis. Okay, so the way I like to do this is to start by drawing a free body diagram of our system, and in this case I'm going to include both the rod and the particle. And if I do that, noting that we're in the horizontal plane, and let me add a little t there, we'll note that the only forces acting on this system, at least as the plane as I look from the top down, are the reaction forces that exist at point O. The most important thing to take away from this is that if we sum moments about point O, we're going to find that that results 0. Which tells me that the angular momentum of this system about point O is actually conserved. In this regard, what we can say is that h about O at state 1, which is a quantity we can compute, has to equal h about O at state 2, which again is a quantity we can compute. To help us out in doing that, I'm going to define a coordinate system. I'll call E sub r to be radially outward, and E sub theta to be perpendicular to that in the direction of increasing angle. And so if I do this, I'll have that h about O at state 1 is going to equal r1 cross m times v1. And if I go ahead and do some substitution here, r1 is going to be the initial distance, which I'll call big R1 in the E sub r direction. I'll cross that with the mass of the particle, which is the weight divided by the gravitational constant g, times its initial velocity. In this case, we told that the particle is initially at rest with respect to the bar, and so the r dot component is initially going to be 0, and so I'm going to get back here a velocity from the r omega component, which is simply r1 times omega 1 in the E sub theta. If you go ahead and expand this cross product, knowing that E sub r cross E sub theta is k, this is going to give me back w over g times r1 squared times omega 1 in the k. We know each of these quantities, and so we know the initial angular momentum of the system exactly. I can then adopt a similar procedure, h about O at state 2, and if I do that, I'll have that's equal to r2 cross m times v2. And if I do the substitution here, what I'll have is that this is equal to r2 in the E sub r cross w over g times r2 times omega 2 in the E sub theta, plus a term that looks like r2 dot in the E sub r. If I go back to the problem statement, you note that we're only looking for the angular speed of the arm, and that's a very good thing because once I do this cross product, E sub r cross E sub theta goes to k, so I'll have w over g times r2 squared times omega 2 in the k, but E sub r cross E sub r goes to 0, and so what we're going to lose is the r2 dot term. That's okay here though because we're just looking for the angular speed. So if I equate these two expressions for angular momentum, I'm going to have that w over g times r1 squared times omega 1 in the k is going to equal w over g times r2 squared times omega 2 in the k. You'll note in this case that the mass cancels out, likewise the k unit vector cancels out, and so I get a final expression for the angular speed of the arm, omega 2, which is given by r1 divided by r2 quantity squared times omega 1. You're given numerical values for each of these quantities, so you can go ahead and plug them in and see how effective this movement in radius is at reducing the speed of the arm. Alright everybody, take care. Best of luck.